Hi there, this is your favorite math learning channel, and I have a cool problem from Python for you. So we have a newly defined sequence, we can call it sequence, with square root of with brackets n. Let's just call this an for simplicity, okay? And so we are given that this an is the closest integer to square root of n. So first we need to make some observations and see what is going on with this sequence. So for example, for a1, so a1 is the closest integer to square root of 1. Square root of 1 is just equal to 1, so it's just 1. For a2 is the closest integer to square root of 2. Square root of 2 is about 1.4, so 1.4 is closest to 1 rather than 2 because it's just less than 1.5. And if I say a3, well, I don't know the value of it, but it's of course bigger than 1.5 because this was just 1.4. So it's bigger than 1.5, so it is just going to be 2 because it's also less than 4. a4, square root of 4 is just 2, so this is 2. So this sequence, it will actually just go like 1, 1, and then for some values of n, it will just be 2, 2, 2, 2s. So we can actually just graph it like with like a step function. So here I think it's just easier to graph it like a continuous function. Well, this is just an integer sequence, but instead of, for example, a1 and a2 is equal to 1, I can just show it like this, but I will just prefer to show it like this, okay? So for example, I have that a1 and a2, 1 and 2 goes to 1. So here, this is my n, and this is an, okay? Just like x and fx, an. And for the ones that are getting 2 is, so it's starting from here. We can just make a gap here for the 3. So these are getting the value of 2. And I don't know up to which point, but I actually can guess it. So if I think of the real line, for example, let's think from 4 to 9, because this one is just getting the value 2, obviously, and this 9 is just getting 3, obviously. So these are like the perfect squares. And so I can just think about the term in the middle. If I add them and divide by 2, I will get 6.5. And actually, if I'm just less than 6.5, I will get, for example, from 6, it's actually just square root of 6.5. We can't know directly that if it's closest to 4 or 9, but we don't care about that. So we can just think about 6 and 7. And indeed, 7 is just closest, square root of 7 is closest to 3, and square root of 6 is closest to 4. I will actually prove this fact because it looks kind of trivial, but it's not that trivial. So we will see how to prove this too. So I know that so then I take the values from 3 up to 6 that is still closest to 2. And then, so let's just extend this a bit. So this is an. And for 3, so this is just going to start from 7. Let's also extend this. So it's going to just start from 7. And again, so similarly, I can say that from 9 to 16, next one is just 16. Let's show it with different one. From 9 to 16. So the middle term is just, if I add them, I get 25, 12.5. So the 12 is closest to 3, so it just goes up to 12. And the next one starts from 13. So this is my sequence, okay? So this was the observation part. And now let's try to formulate this function, its sequence. So here we have some jumping up parts. I will call this level up, okay? We have some level ups. For example, we level up after 2. We level up after 6, okay? Let's write this level ups. So level up at, so I have level up at 2, also at 6, also at 12. Well, I can actually just realize here that first of all, there are two ways to understand this. First of all, that this width is just 1, and this width is just 3. So this width from 3 to 6, this width is 1, 3, 5. So this is actually just giving me, so it goes like 1, 3, 5. These are all of the odd numbers. So the next one is just going to be 7, for example, plus 7 to the next one, but plus 7 to the 13. So it is going to be 20. And I can actually just observe that this is 1 times 2. This is 2 times 3. This is 3 times 4. And this is 4 times 5. And it will always continue like this, because these are actually just like triangular numbers. So here what I can do is that, so I found that the times that I have a level up, so I have a level up when I'm at f4 at a number that is like n, which is in the form of n times n plus 1. So I know that so n, well, n is usually just equal to the next term. Here these lines are just going to get wider and wider, because here I added 3, here I added 5, 7. So these lines are just going to get wider and wider. N is going to be equal to n plus 1 usually, but when is it not going to be equal is at the jump, at the level ups. So when I level up, n is not going to be equal to n plus 1. For example, n is equal to 12, but n plus 1 is not going to be equal to a12, is not equal to a13. So for n's that are leveling up, this equation will not satisfy. For n, this is going to be true. For n is in this form, m times n plus 1. Let's open this, m squared plus n. So now this is actually very important for the n. So we found when do we have a level up, and what does that mean? So now let's try to just write values of it. So I have that a1, a2, a3, a4. Let's continue a bit more. a5, a6. Well, I know just all of these, but or let's don't write them here. And now let's go to the problem. So this is my question. Let's say this is equal to s, and now let's rewrite it. So I have s. So of course I don't want to just calculate the top part and divide it by n, because this is not so nice, since this is just inverse of this thing, and they may not have a nice sum. So let's kind of combine these and add with this one. So I'm going to say that I have, so this is n greater, and going from 1 to infinity, I will just say greater or equal than 1. So I have 2 to the minus n from this thing. And this is just plus an. Let's write an. Wait, there's no bracket. Or I can put bracket and put parentheses. It's not so important. And for the second part, well, I'm assuming that this is convergent, because it of course is convergent. Why? Because if I think about both of the parts, for example, I can say that 2 to the an over 2 to the n. So I know that an is close to square root of n. It's not really bigger than that. For example, I can say, of course, this thing is just less than n. So this thing is just less than n. Oh, then it's not convergent. But it's more or less close to just square root of n. So it will be, this is like almost same as saying 2 square root of n over 2 to the n. So this is just going to be 2 to the minus n over 2. And this is just going to be convergent if I add them. Okay. these series are convergent. It's horrible writing. So now I have this thing, and for the second part, I'm just separating these sums. Okay, it's why I talked about convergence. If it's not convergent, I can't separate them. And for this part, this is just going to be 2 to the n. So again, it's of course just minus n. And this is also minus n. So I can, again, just put it with parentheses. It's not so important, but wait. I take it inside n plus an. Okay, cool. So this is my required sum. And so now let's directly write n minus an and n plus an values. So I'm gonna write the sequence of n plus an. Okay. Let's say it like this. So I'm gonna find values of this thing. Okay. So for n is equal to 1, I found that it's just 1. So this is 1 plus 1. For n is equal to 2, this is 1 plus, and an is still 1. So this is 1 plus 1. Sorry, n is 2, 2 plus 1. For n is equal to 3, this thing is 2, and n is 3. So it's just 3 plus 2. And next time 4 plus 2. And it's 2 up to here, up to 6, we just figured that out. So it's just gonna be like 4 plus 2, 5 plus 2, 6 plus 2, and at the level up, we level up at 7. This is 7, and this thing is just gonna be 3 plus 3. So it will just go like this. And now if I just take this value, so this goes like 2, 3, 5, 2, 3, 5. So I saw that when I'm at the level up part, so I leveled up after 2, after n is equal to 2, I skipped 4. So this is important. And now if I continue 5, this is 6, 7, 8, and 10. So I also skipped 9. Okay, cool. Well, yeah, this is kind of obvious. So it is the case that we're skipping the perfect squares here. So I can actually say that these terms are just all of the numbers from 2 except for the just perfect squares. I will consider this thing when I'm adding them. And let's also do n minus an, because the first part is actually n minus an. So this is just, the signs are just going to be minus. So 1 minus 1 is just 0, 2 minus 1 is 1, 3 minus 2 is also 1. And this time it seems like maybe I will repeat them. 4 minus 2 is 2, 3, 4, and this is also 4. Okay, cool. And now, so when I'm at the perfect square, I'm just skipping the perfect squares extra. So this is actually perfect because I will add them, and here I'm missing perfect squares, and here I have them extra, except for the one case because I don't have anyone at all here. So now let's add them. And I also have minus in front of them. So here everything will just be minus. So let's put minus signs. It's not so important. So now if I go here, let's write it here. So I'm gonna have that. So I have n minus an's here. So I have this sequence. So if I try to write this, well, I have all powers of 2. N is greater or equal than, let's say, 0, because I'm starting from 0. I have even 2 to the 0. This is just 2 to the n. If I say this, I'm going to get 0, 1, 2, 3, 4. It's just going to go like this. And I indeed have all of them. But I also have these terms again. So this is actually just adding all of the perfect square powers of 2. So I can say this is greater or equal than 0. Or let's say this is from 1. 2 to the n squared. So basically, if I put 1, I'm going to get 1. If I put 2, I'm going to get 4. I'm adding powers of 2 to the perfect squares. Cool. So this was the first part. This is equal to that. And if I continue, so for this stuff, well, again, it's just all of the integers except for the perfect squares. So I can say this is just, I'm adding everything. Well, this time it starts from 2. So let's say n is greater or equal than 2 to the n, because I just have all of the powers. Also, this is minus. And this is also minus, because I forgot this minus, okay? So all of these values are just minus. And so this is just gonna give me the first part of this, and I'm missing perfect squares here, so it is just gonna be minus. So I'm missing perfect squares, but I start missing from n is equal to 2, right? I'm starting from n is when the power is 4, so I can say this is also greater or equal than 2 to the n minus n squared. So this is, let's show it with a line. So this is equal to that, and this first part was equal to this. Well, I'm almost done, because now I can see that these two are just gonna end up being something nice. So 2 to the minus n, this is just adding powers of 2. This is just geometric, okay? And I can say that, well, this is just 1 over 1 minus x. So this is just 1 over 2 to the n. Okay, so this is geometric, and this will just go to 1 over 1 minus x, 1 over 1 minus 1 over 2, which is just 2. So this thing will just go to 2. So in the end, I will just write my answer. This is 2. And for this part, well, I will just combine it with this. So let's forget it for now. And for this part, this is n starting from n is greater or equal than 2. So I can just imagine like, oh, I didn't take the first 2 terms. Or I can just take it into 1 over 4 parentheses. It doesn't matter. So here, basically, I have that I don't have the term when n is 0, which is going to give me 1. And I don't have the second term, which is going to give me just 1 over 2. So I don't have this. So this is actually just 2 minus this stuff, which is equal to, so this is 3 over 2. I'm going to get 1 over 2. So this sum is just equal to 1 over 2. I'm writing huge. And for the next of the next terms, well, this is just, they're just making 0, right? They are basically the same thing with opposite signs. So this is going from 2 to infinity, and this is going from 1 to infinity. So I will have canceled all of the terms going from 2 to infinity, and I will only get the first term of this thing, which is when I put n is equal to 1, I'm going to get, again, just 2 to the minus 1. So this is also plus 1 over 2. And that's it. So here I'm just going to get 3. So this is our answer, and this is the end of the question. Now, well, I skipped a part that, so I said when I was solving the problem that if you're at the middle, if you go to one, well, actually just half to the left, you're going to get closer to this side if you take square root of it. And if you just get one bigger. So I said that this is just perfect spot, perfect like kind of balance for the square being closest to square root of n. Let's also prove this now. So what I want to show that, so for example, let's again write the case with 4 and 9. So I want to show that the number that is between them, so and if I want to generalize this, let's say this is m squared, and this is just m plus 1 squared. Here m is 2, for example. So I want to get the middle term, okay? So this is 6.5, and I will go to 6, okay? Or I can go to 7. So, and how do I, first of all, how do I get the middle term? 6.5 is just adding, and it's just their average, right? So I have m squared plus m plus 1 squared. So if I add them and divide by 2, I'm going to get the middle term, okay, 6.5. So this is going to give me the 6.5. And so, well, also, so if I think about number squares, for example, it goes from 4, 9, 16, 25. So it's just like 2 squared, then 3 squared, 4 squared. So since your number is just increasing by 1, it's even, odd. And the powers doesn't change it. So these numbers are always just even, odd. So all the time, one of the ends is gonna be even and one of the ends is gonna be odd. It can be opposite order. 9 could be here and 16 could be here too, but it doesn't matter. So this thing is actually always odd because we are adding even and odd. So this thing will never be an integer. And also, so I want to get the 6, so I can just subtract 1 and then divide by 2. So this means basically just subtracting -1/2, which is just guaranteeing that I will take the term that is closest to the middle but on the left side. So this is actually how to formulating get 6, okay? So what I want to show is that if I get square root of 6, this is closest to m squared, which is actually here, it's not m squared, but square root of m squared. So I want to show that this is closest to m. Is this really closest to m? So how can I do that? Or yeah, so I will try to show that this is just closest to m. And so, well, I can think of it in two ways. I can either compare it with m or m plus 1. So for example, if I think a number that is, for example, I have a number 35 point, let's say 4 or 5, whatever. If this thing is just bigger than 5, this is just going to be closer to 36, right? And in this way, this is just going to be closer to 35. So actually, if this thing is just less than 5, which means that actually, if I just take a number and subtract 1/2, so I say, for example, 35 point something, let's say 4, if I subtract 1/2, and if this thing is just less than 35, I'm guaranteeing that this thing was less than 5, okay? So even if I don't know this thing, if I know that this thing is just less than 35, I will make sure that this thing was less than 5. If it was 5, the equality would hold, but it doesn't matter. So my goal is I'm just going to subtract 1/2, and I will see if this is actually less than m. So what does that mean again? That if I take this, if I have a number and I subtract 1/2, if this is less than the number that we want to compare, this means that the number, for example, m is a number, it's like m.4, m.45, m.3, but it's not m.5. So it's not closer to m plus 1, but it is closer to m. So I want to show this inequality. Well, it's actually very easy. I can just send this to the other side. Let's just delete this, put it here, and square all sides. So I'm just gonna get that. Also, if I open this thing, so this is m squared, and this is also m squared plus 2m plus 1. So ones will cancel out, and I will have m squared, 2m squared, and plus 2m. So I can just cancel it with 2. So this is just gonna be m squared plus m. So I'm just rewriting it. I didn't do anything now. Is less than m plus 2. So I want to show this is true. So, well, since this is just positive, this is going to be true if and only if I'm just going to take squares on both sides. M squared plus m is less than m squared. So I'm just squaring it. So this is going to be m, because this thing times this times 2 plus 1/4. And of course this is true because it's the same thing plus 1/4. So this is true. For example, you could, if you want, you could just start from here and go to here by just taking square root of all sides, because they are, again, just all positive. And so this is very obviously true. So this is true. So this means that if you, again, just like how I formulated, if you take a number that is in the middle of two perfect squares, and if you just go to half left or half to the right, you will get to the, so if you take square root of 7, you will be closer to square root of 9. And if you go to left, you will just be, you're just guaranteeing this for any two perfect squares. For example, if you're between 400 and 441, which is 20 and 21 squared, if you take, if you just take their average term, it is going to be 420.5. For example, you're guaranteeing that 420 is just about, let's say it's about just 20 point something, but less than something that is sorry, point something that is less than 5, for example 4. So here I actually just show this with graph 2. Here I actually wrote 5, but yeah, this is just less than 0, because yeah, I just swapped sides. For example, square root of 420 is indeed, oh, this is very close, 49. But even if I make the numbers very big, it will just actually just get closer and closer to the 5, but it will never be 0.5. Okay, and that's a good place to stop.